At 12:15 hours on November 8, 1931, in a nondescript hotel room in the Belgian border town of Verviers, a mid-level German bureaucrat named Hans Stylo Schmidt slides a leather briefcase across a wooden table toward French intelligence officer Rodolphe Lemoyne. Inside the case lie two documents that will change the course of the 20th century: the operating manual for Germany's new Enigma cipher machine and a month's worth of daily key settings. Schmidt, embittered by financial hardship and resentment toward the German military establishment that denied him advancement, accepts 10,000 Reichsmarks for his betrayal. He receives the codename Ashes in German, a fitting epitaph for what he sets in motion. This transaction represents the first crack in what Nazi Germany believes to be an unbreakable code. Within 11 years, this machine and the desperate Allied effort to defeat it will determine whether Britain starves, whether the Atlantic convoys survive, and whether millions more will die before victory arrives. This is not the story of how one genius mathematician broke Enigma. This is the story of how three nations, dozens of brilliant minds, one critical spy, and a series of increasingly improbable captures created the intelligence advantage that historians estimate shortened World War II by 2 to 4 years and saved 14 million lives. The Enigma machine that German forces adopt in the late 1920s appears, at first glance, like an unusually complicated typewriter. The standard military Enigma I weighs approximately 12 kilograms and measures 28 centimeters wide, 34 centimeters long, and 15 centimeters high when closed in its wooden carrying case. But this deceptively compact device contains one of the most sophisticated encryption systems ever deployed for field use. At its heart sit 3 rotors, metal and black plastic cylinders, each containing 26 spring-loaded terminals on one side and 26 flat circular contacts on the other. Each rotor contains unique internal wiring that scrambles the 26 letters of the alphabet in a fixed but different pattern. When an operator presses the letter A on the keyboard, an electrical current flows through the rotors, is reflected back through a reflector component, passes through the rotors again in reverse, and illuminates a letter on the Lamboard above, perhaps F or Amio, or any letter except A itself. This fundamental weakness that no letter can ever encrypt to itself becomes crucial to Allied code-breaking efforts, though the Germans never recognize it as a flaw. After each keystroke, the rightmost rotor advances one position, changing the electrical pathway and producing a different substitution for the same letter. When the first rotor completes a full rotation, it causes the middle rotor to advance one position, and when the middle rotor completes its rotation, the leftmost rotor advances. This creates what cryptographers call polyalphabetic substitution, with a period of 16,900 characters before the configuration repeats. But the Wehrmacht adds additional layers of complexity. The rotors themselves are removable and interchangeable. Military Enigma machines come equipped with 5 different rotors, labeled I through V, each with unique internal wiring. Operators select 3 rotors and arrange them in any order, creating 60 possible rotor combinations. Each rotor possesses an adjustable ring setting, a numbered ring around its circumference that can be set to any of 26 positions, multiplying the possibilities by 17,576. The most devastating complication arrives in 1930, when German military Enigma adopts the plugboard, the Steckerbrett. This component sits in front of the keyboard and contains 26 sockets corresponding to each letter. Before the signal enters the rotors, it passes through cables that swap pairs of letters. German protocol requires operators to connect 10 cables, swapping 20 letters and leaving 6 unchanged. The number of possible plugboard configurations alone exceeds 150 trillion. When operators combine rotor selection, rotor order, ring settings, rotor starting positions, and plugboard connections, the German Enigma produces approximately 159 million possible daily key settings. German cryptographers believe this makes Enigma mathematically unbreakable. They are wrong, but their miscalculation requires a particular combination of mathematical genius, international cooperation, and operational mistakes to exploit. In September 1932, in a converted office building on Poznań Street in Warsaw, a 27-year-old Polish mathematician named Marian Rejewski stares at the documents French intelligence has purchased from Hans Thilo Schmidt. The Polish Cipher Bureau has recruited Rejewski and two colleagues, Jerzy Rokicki and Henryk Zygalski, specifically for their expertise in permutation theory and group theory, mathematical disciplines that prove essential for understanding Enigma's internal logic. Poland, sandwiched between Nazi Germany and Soviet Russia, possesses urgent motivation to break German communications. The French have shared Schmidt's documents with their Polish allies, but failed to make progress themselves. What Rejewski possesses that the French lack is a fundamental insight. Enigma is not primarily a linguistic puzzle to be solved through frequency analysis and pattern recognition. Enigma is a mathematical problem requiring algebraic solutions. The documents from Auschwitz provide two critical pieces: the wiring patterns for the commercially available rotors and examples of daily key settings. But they do not reveal the complete military Enigma's internal structure, particularly the rotor wirings used in the newer military models. Rejewski approaches this problem through pure mathematics. He constructs equations based on the machines, known electrical flow patterns, and the principle that Enigma's encryption must follow certain mathematical symmetries. German operating procedures in this period require radio operators to transmit a message key, the rotor starting positions, for that specific message at the beginning of each transmission. To ensure accuracy, operators type the three-letter key twice, encrypted using the daily key setting published in codebooks. This means the first 6 letters of each message represent the same 3 letters encrypted twice, with rotors advancing between repetitions. This seemingly sensible precaution proves catastrophic. Rejewski exploits this repeated message key through a technique that examines the relationship between the first and fourth letters, the second and fifth letters, and the third and sixth letters across hundreds of intercepted messages. These relationships create what mathematicians call chains that reveal information about the rotor wirings independent of the daily settings. After weeks of intensive calculation, Rejewski successfully determines the internal wiring of all 3 military rotors. By December 1932, the Polish Cipher Bureau achieves regular breaks into German military Enigma traffic. For 7 years, from 1932 to 1939, Poland reads German military communications, while Germany remains completely oblivious. The Poles developed several techniques to accelerate the code-breaking process. They construct a device called the bomba cryptologica, not a weapon, but a machine consisting of 6 interconnected Enigma machines that could mechanically test rotor positions to identify daily keys. Each bomba weighs approximately 100 kilograms and can test all possible rotor arrangements in approximately 2 hours. Rokicki and Zygalski develop additional methods, including the Zygalski sheets, large perforated sheets that allow analysts to overlay patterns and identify consistent rotor starting positions. These techniques work effectively until September 15, 1938, when German radio operators cease the double encryption of message keys and adopt a more secure protocol. This procedural change, combined with Germany's introduction of 2 additional rotors in December 1938, overwhelms Polish capabilities. On July 25, 1939, 5 weeks before Germany invades Poland, representatives from the Polish Cipher Bureau meet with British and French intelligence officers in the Kabety Woods south of Warsaw. In a moment of remarkable generosity born of desperation, the Poles provide their allies with complete technical information about their Enigma-breaking methods. Rejewski's rotor wirings, blueprints for the bomba machines, and actual replica Enigma machines constructed by Polish intelligence. British cryptanalyst Dilly Knox, who has struggled for years to penetrate Enigma, reportedly weeps when he sees the Polish solutions. This transfer represents one of the most consequential intelligence exchanges in history. Without Polish mathematical breakthroughs, British efforts at Bletchley Park would have started from absolute zero in September 1939 instead of building on 7 years of Polish experience. The estate at Bletchley Park, located 50 miles northwest of London at a critical railway junction connecting Oxford, Cambridge, and London, becomes operational as the Government Code and Cipher School on August 14, 1939, 18 days before Britain declares war on Germany. The Victorian mansion and its surrounding grounds appear unremarkable, a country house with architectural pretensions surrounded by temporary wooden huts. Yet within these buildings, an unprecedented concentration of mathematical, linguistic, and analytical talent assembles to attack what remains history's most sophisticated military cipher system. Alan Turing arrives at Bletchley Park on September 4, 1939, the day after Britain's declaration of war. The 27-year-old Cambridge mathematician brings a unique perspective shaped by his 1936 paper, Uncomputable Numbers, which laid theoretical foundations for modern computing. Turing recognizes that the Polish bomba concept can be dramatically expanded. His crucial insight, rather than simply replicating Enigma rotors mechanically, a machine could test logical contradictions emerging from cribs, known or guessed plaintext phrases. German military communications follow predictable patterns. Weather reports consistently contain the word wetter. Naval messages regularly include Wetterübung. Position reports invariably reference grid coordinates. When cryptanalysts guess a phrase's position in an encrypted message, they create a crib. Turing's bomb machine, named after the Polish bomba, but fundamentally different in operation, exploits these cribs by testing whether particular rotor settings create logical impossibilities due to Enigma's reflector property. The first prototype bomb, christened Victory, becomes operational on March 14, 1940. The machine stands approximately 2 meters tall, 2 meters long, and 1 meter wide, weighing nearly 1 ton. Its face contains 108 rotating drums arranged in 36 sets of 3, each set mechanically simulating one Enigma rotor configuration. When activated, Victory sounds like dozens of knitting needles rapidly clicking, producing what workers describe as a herringbone pattern of sound that indicates the drums rotating at high speed. But Victory proves relatively inefficient. Gordon Welchman, Turing's colleague in Hut 6, develops a critical enhancement called the diagonal board that exploits the reciprocal nature of Enigma's plugboard. If the plugboard swaps A to M, it must also swap M to a Welchman's diagonal board, creates additional logical constraints that reduce false, stops incorrect solutions that the machine identifies by a factor of 10 or more. The improved Turing-Welchman bomb enters production in August 1940. By 1942, Bletchley Park operates 49 bombs. By 1945, that number reaches 211 British bombs, plus 121 American-built bombs operated by the U.S. Navy. Each bomb requires 3 trained operators, typically members of the Women's Royal Naval Service, called WRENs, working 8-hour shifts. A single bomb run testing one crib against possible daily keys typically requires between 12 and 20 minutes, though some runs continue for hours without finding a solution. The organizational structure at Bletchley Park divides work into specialized huts. Hut 6, led by Welchman, attacks German Army and Air Force Enigma. Hut 8, led by Turing, and later by mathematician Hugh Alexander, focuses on German naval Enigma, the most difficult variant. Hut 4 translates and analyzes Army and Air Force decrypts. Hut 3 handles naval intelligence. Additional sections manage interception, traffic analysis, and the distribution of intelligence to military commanders under the codename Ultra. Hut 8 faces particularly daunting challenges. The Kriegsmarine employs more sophisticated procedures than other German services, changing keys more frequently and using specialized codebooks called Kenngruppen to disguise message indicators. The naval Enigma also utilizes different rotors with more complex notch positions. Breaking naval Enigma requires not just mathematical brilliance, but operational intelligence, actual German materials captured from vessels or U-boats. Joan Clark, one of the few female cryptanalysts at Bletchley Park, becomes one of Hut 8's most valuable members. Hugh Alexander later describes Clark as one of the best Banburists in the section. Banburismus named after the town of Banbury, where special perforated sheets are printed represents a statistical method for narrowing down possible rotor orders before running time-consuming bomb tests. Clark's skill at this painstaking work directly contributes to breaks that save Allied shipping in the Atlantic. The mathematical method behind Banburismus involves analyzing the statistical properties of overlapping message texts encrypted with the same rotor order but different starting positions. By comparing the frequency of certain letter combinations across multiple messages, skilled analysts can identify with reasonable probability which rotor order the Germans are using that day. This preliminary analysis reduces the number of bomb runs required from potentially hundreds to perhaps a dozen, making daily breaks practically achievable. Yet even with these methods, success remains uncertain. German procedural discipline varies dramatically between services. When operators follow proper security protocols using random message keys, varying message lengths, avoiding predictable phrasing, Bletchley Park struggles. When operators become lazy or predictable, as many do as the war progresses, the Codebreakers thrive. At approximately 10:20 hours on May 9, 1941, in the cold waters south of Iceland, the British destroyer HMS Bulldog commands U-110 to surface after a sustained depth charge attack. The German submarine, commanded by Captain Lieutenant Fritz Julius Lemp, wallows disabled on the surface, with pressure hull compromised and electrical systems failing. Lemp orders his crew to abandon ship and to activate the scuttling charges that will send U-110 to the ocean floor before the British can board her. But the scuttling charges fail to detonate properly. As the German crew frantically rows toward HMS Bulldog, Sub-Lieutenant David Baum leads a boarding party of 8 men across to the slowly sinking U-boat. What they find transforms the Battle of the Atlantic. An intact M3 Enigma machine, complete with rotors in position, current daily key sheets, and codebooks including the crucial Kurs signal heft, the short signal book that allows German U-boats to transmit compressed tactical reports. Baum and his men work with desperate speed, passing documents and equipment up through the conning tower while seawater rises below. They recover everything not bolted down: charts, logbooks, technical manuals, and most valuable of all, the Enigma materials. Uchum says Bulldog then takes U-110 in tow, but the submarine sinks before reaching port. Crucially, German authorities conclude that U-110 sank with all hands before the British could board her. This misapprehension proves catastrophic for German naval security. The captured materials arrive at Bletchley Park on May 13, 1941. For the first time, Hut 8 possesses complete, current German naval keys and procedures. Within days, Bletchley Park achieves its first sustained break into Kriegsmarine traffic. For the next month, British intelligence reads German U-boat communications almost in real time, allowing convoy routing officers to divert merchant shipping away from Wolf-Pack concentrations. In that single month, the tonnage of Allied shipping sunk by U-boats drops by 50% compared to April 1941. But the advantage proves temporary. German naval procedures require new keys monthly, and each month presents a fresh challenge. The basic problem remains the same: identify rotor order, ring settings, and plugboard connections from encrypted traffic, but without current materials. This requires between 12 and 24 hours of intensive work by dozens of personnel. Additional captures follow. On August 27, 1941, British forces board the German trawler Krebs off Norway and seize Enigma materials. In September 1941, U-boats U-570 and U-111 provide additional intelligence. The weather ship Lauenburg, captured in June 1941, supplies another complete set of keys and codebooks. Each capture provides weeks or months of insight into German procedures and dramatically reduces the time required to break subsequent traffic. The most consequential capture occurs not at sea, but on land. On October 30, 1942, British forces advancing through North Africa overrun a German signals intelligence unit and capture not just Enigma machines, but detailed documentation of how the Germans themselves approach cryptanalysis. This meta-intelligence understanding how the enemy thinks about code security proves as valuable as the codes themselves. Yet these captures create a strategic dilemma. British intelligence must protect the secret that Enigma has been broken. This requirement generates elaborate deception protocols. Ultra-intelligence cannot be acted upon directly. When Ultra reveals a U-boat's position, the Royal Navy must first dispatch reconnaissance aircraft to discover the submarine before attacking it, creating a plausible non-cryptographic explanation for the intercept. When Ultra identifies supply convoys in the Mediterranean, RAF bombers must first conduct visible search patterns before coincidentally finding and attacking their targets. These deception protocols sometimes fail tragically. In November 1941, Ultra intelligence reveals that a large German convoy is heading toward Tobruk. The Royal Navy attacks immediately before establishing cover reconnaissance and destroys all 4 supply ships. German signals intelligence analyzes British radio patterns before and during the attack and concludes that the British possessed advance intelligence of the convoy's route and timing. Admiral Karl Dönitz, commander of Germany's U-boat fleet, initiates an investigation into Enigma security. The investigation proves both thorough and blind. German cryptographic experts test whether captured Enigma machines could provide an advantage. They conclude correctly that a captured machine alone reveals nothing about daily key settings, which change every 24 hours according to codebooks. They test whether the Enigma algorithm itself contains mathematical weaknesses. They conclude incorrectly that the number of possible settings makes systematic cryptanalysis impossible without impossibly large computational resources. They never imagine that the British have constructed 211 one-ton electromechanical machines dedicated exclusively to testing Enigma settings, each capable of checking thousands of configurations per hour. The investigation exonerates Enigma. Dönitz attributes British successes to direction finding, traffic analysis, and espionage, but never to systematic cryptographic breaks. This conclusion seals Germany's fate. Had the Kriegsmarine abandoned Enigma in late 1941 or early 1942, the Battle of the Atlantic's outcome becomes unpredictable. At midnight on February 1, 1942, German U-boats operating in the Atlantic switch from the 3-rotor M3 Enigma to the new 4-rotor M4 variant, codenamed Shark by Bletchley Park. Within hours, ultra-intelligence from U-boat traffic ceases completely. The 10-month period that follows represents the darkest chapter of the Battle of the Atlantic and the greatest crisis Bletchley Park faces during the entire war. The M4 Enigma represents a significant technical advancement. The 4th rotor fits in the same space as the 3-rotor version by making the 4th rotor and the reflector thinner. This 4th rotor initially sits in a fixed position, essentially functioning as a rewirable reflector, but its 26 possible starting positions multiply the number of possible daily keys by 26. More critically, the 3-rotor bombs at Bletchley Park cannot test 4-rotor configurations without testing each of the 26 4th-rotor positions separately, multiplying the required processing time by 26, and making daily breaks practically impossible with existing resources. The immediate impact proves devastating. Without current ultra-intelligence, a Allied convoy routing in the Atlantic reverts to educated guesswork. In March 1942, U-boats sink 567,000 tons of Allied shipping 95 ships. In November 1942, U-boats sink 729,000 tons 119 ships. The monthly figures rival or exceed the worst months of 1940. At this rate of loss, Britain's strategic situation becomes untenable. The island nation imports 55 million tons of material annually: food, fuel, ammunition, raw materials. If U-boats maintain this kill rate, Britain cannot continue the war beyond mid-1943. At Bletchley Park, Hut 8 attacks shark with desperate intensity. The fundamental mathematics remain unchanged, the same Banbury's techniques, the same crib-based logic, but the exponentially larger problem space means that even finding promising rotor orders requires weeks instead of days. Alan Turing develops new statistical techniques to extract information from shorter message fragments, but progress comes slowly. Joan Clark and Hugh Alexander work exhaustive shifts testing increasingly speculative hypotheses. The breakthrough arrives not from mathematics, but from German error and Allied opportunism. On October 30, 1942, U-559 sinks in the Mediterranean after sustained depth charging by H.M. Spitard. 3 British sailors, Lieutenant Tony Fasson, able seaman Colin Grazier, and 16-year-old canteen assistant Tommy Brown swim to the sinking submarine and climb inside to retrieve documents. They pass codebooks and cipher materials up through the conning tower as water rises around them. Fasson and Grazier drown when U-559 suddenly plunges to the seafloor, but the materials they recovered reach Bletchley Park. The U-559 capture provides the Kurssignalheft and Wetterkursschlüssels, the short weather code book. This specialized code book allows U-boats to transmit weather observations in highly compressed format. Crucially, these weather reports follow predictable patterns and include standardized phrasing that Hut 8 can use as cribs. With these cribs and captured materials showing current key structures, Bletchley Park achieves its first break into 4-rotor shark traffic on December 12, 1942, 10 months after the blackout began. But breaking shark once doesn't solve the fundamental problem. Each day requires fresh breaks, and the 3-rotor bombs remain inadequate for reliably fast solutions. The answer comes from British engineering and American industrial capacity. British Tabulating Machine Company at Letchworth builds new 4-rotor bombs beginning in June 1943, and the U.S. Navy's cryptologic section constructs 121 bombs at a facility in Dayton, Ohio. These American machines employ different engineering principles using electronic relays instead of electromechanical drums and process far faster than British designs. By May 1943, sufficient bomb capacity comes online to achieve daily breaks in shark traffic within a few hours. The impact on the Battle of the Atlantic appears almost immediately. In April 1943, U-boats sink 235,000 tons of Allied shipping. In May 1943, that figure drops to 165,000 tons, and 41 U-boats are lost, catastrophic casualty rates that Admiral Dunitz calls Black May. In June, only 18,000 tons sink, while the Allies destroy 17 more U-boats. By July 1943, Dunitz orders his U-boats to withdraw from the North Atlantic convoy routes, effectively conceding defeat in the campaign that Adolf Hitler called the only thing that ever really frightened me during the war. The statistical reversal proves remarkable. From September 1939 through January 1943, U-boats sink approximately 7.5 million tons of Allied shipping, while losing 154 submarines, a ratio of nearly 50,000 tons sunk per U-boat lost. From June 1943 through December 1943, U-boats sink approximately 300,000 tons, while losing 141 submarines, a ratio of 2,100 tons per U-boat lost. The Battle of the Atlantic has not merely turned. It has collapsed. Ultra-intelligence deserves substantial, but not exclusive credit for this reversal. Improved convoy escort tactics, long-range aircraft equipped with centimetric radar, HFDF direction-finding equipment, and escort carriers all contribute to Allied success. But Ultra provides the strategic intelligence that allows these tactical capabilities to find their targets. Knowing where U-boats concentrate allows convoy routing to avoid wolf packs and enables escort groups to hunt submarines in predictable patrol areas. The story of Enigma extends far beyond the Battle of the Atlantic. German forces employ Enigma variants across every theater, and Bletchley Park develops specialized sections to attack each variant. The Luftwaffe's Enigma proves generally easier to break than naval versions due to less rigorous operational security. German Air Force operators frequently use standardized phrases, keine besonderen Ereignis, nothing special to report, that provide excellent cribs. By mid-1940, Bletchley Park achieves regular breaks in Luftwaffe keys. This intelligence proves crucial during the Battle of Britain. Ultra cannot predict specific Luftwaffe raids with enough precision to scramble fighters to exact intercept points, but it reveals German strategic intentions, target priorities, and bomber strengths. When Hermann Göring orders the Luftwaffe to shift from attacking RAF airfields to bombing London in September 1940, Ultra identifies this strategic change, allowing fighter command to rest and rebuild. Intelligence historians debate whether Britain would have lost the Battle of Britain without Ultra, but they agree Ultra significantly reduced British aircraft and pilot losses during the critical summer of 1940. In North Africa, Enigma intelligence, combined with breaks into Italian codes, provides Field Marshal Bernard Montgomery with unprecedented insight into German and Italian capabilities. Before the Battle of El Alamein in October 1942, Ultra reveals precise German fuel shortages, identifies which panzer divisions remain combat effective, and shows that Erwin Rommel has returned to Germany for medical treatment. Montgomery plans his offensive around this intelligence, concentrating forces at points Ultra reveals as weakly defended and timing attacks to exploit confirmed German logistics difficulties. The Wehrmacht introduces additional Enigma variants as the war progresses. The German Army General Staff employs a variant with an adjuster ring that allows the reflector to be set in 26 different positions, dramatically complicating cryptanalysis. German military intelligence. The Abwehr uses machines without plugboards, but with 4 rotors selected from a larger set, creating different mathematical challenges. The Gameschreiber teleprinter cipher system represents an even more sophisticated German encryption technology, broken primarily through the Colossus computers developed at Bletchley Park's Newmanry section. Yet the Germans never completely abandon Enigma or develop systematic doubts about its security. Post-war interrogations reveal remarkable German confidence in their cipher systems. General Alfred Jodl, Chief of Operations for the Wehrmacht, states after his capture that he considered Enigma absolutely secure and never imagined Allied forces possessed sophisticated cryptanalytic capabilities. Admiral Karl Donitz refuses to believe Ultra revelations, even when presented with evidence during Nuremberg proceedings. This confidence stems partly from Germany's own cryptanalytic failures. German signals intelligence breaks some Allied codes, particularly merchant shipping codes, and certain diplomatic ciphers, but never penetrates the highest level, British or American military codes. The Germans project their own cryptanalytic limitations onto the Allies and conclude that systematic breaks into military-grade ciphers require impossibly large resources. They fail to grasp that Britain and the United States commit precisely those impossible resources. By 1945, Bletchley Park employs approximately 9,000 personnel. The U.S. Army's signals intelligence operation employs 12,000. The combined Allied cryptanalytic establishment represents an industrial-scale intelligence operation unprecedented in history. The Germans operate signals intelligence with perhaps 3,000 personnel total, and never imagine their enemies outspend them by factors of 5 or 10 to 1. The operational security surrounding Ultra proves remarkably effective. Churchill restricts Ultra distribution to a small number of commanders and intelligence officers, all briefed on the absolute requirement for secrecy. Ultra intelligence arrives via special liaison units, military intelligence officers who deliver reports directly to commanders and retrieve them after reading. Nothing may be written down at field headquarters. Commands based on Ultra must always include plausible alternative justifications. This security occasionally produces surreal situations. During the North African campaign, Ultra reveals the exact route of a convoy carrying Erwin Rommel from Europe to Africa. Churchill proposes having the RAF intercept and kill Rommel. The plan is abandoned not from moral qualms, but because the calculated risk to Ultra secrecy exceeds the strategic value of eliminating one commander. In another instance, Ultra identifies the location of Albert Speer, Hitler's armaments minister, at a conference in France. British intelligence concludes that an assassination would prompt German investigation into how the British located Speer with such precision, potentially threatening Ultra security. The intelligence derived from Enigma becomes so valuable that military commanders begin to rely on it excessively. In 1943, British intelligence officers notice that some commanders refuse to act on non-Ultra sources, assuming that if Ultra hasn't confirmed information, the information must be false. Intelligence agencies develop the term Ultra-itis to describe this dependency and periodically remind commanders that Ultra represents one intelligence source among many, and that gaps in Ultra coverage don't necessarily indicate gaps in enemy capabilities. The secret of Enigma remains classified for nearly 3 decades after the war ends. The British government seizes all Enigma machines in 1945 and distributes them to Commonwealth nations and colonies with assurances that they provide secure communications. Several countries, including post-colonial governments in Africa and Asia, use Enigma variants well into the 1960s, completely unaware that Britain reads their traffic with ease. The irony proves profitable. British intelligence continues exploiting Enigma for 15 years after Germany's defeat. Not until 1974, when RAF officer F.W. Winterbotham publishes The Ultra Secret, does the public learn about Bletchley Park's work. Winterbotham's account contains errors and exaggerations, but breaks the official silence. Within months, Polish cryptologists Marian Rejewski and Henryk Zygalski published their own accounts, revealing the Polish contribution that British accounts had omitted. The historical record begins to assemble itself from fragments as former codebreakers emerge from enforced silence. The impact of Enigma intelligence on the war's outcome remains debated. According to historian F.H. Hinsley, official historian of British intelligence during World War II, Ultra intelligence shortened the war by 2 to 4 years. This estimate derives from analysis of specific campaigns, particularly the Battle of the Atlantic, where Ultra provided decisive advantages. Without Ultra, the U-boat campaign likely continues through 1944 or 1945 at unsustainable loss rates, potentially forcing a negotiated peace or delaying the invasion of Europe by years. But quantifying Ultra's contribution proves methodologically challenging. How many ships sailed safely because convoy routing avoided U-boat concentrations revealed by Ultra? How many RAF pilots survived because Ultra identified Luftwaffe strengths and intentions? How many Allied soldiers lived because Montgomery's offensive at El Alamein exploited intelligence about German weaknesses? The counterfactual history of a war fought without Ultra stretches beyond calculation. What remains undeniable Enigma represents the first industrial-scale cryptanalytic effort in history. Bletchley Park pioneers methods that become foundational to modern intelligence work specialized teams, attacking specific problems, mechanical computation to accelerate cryptanalysis, operational security protocols for protecting sources, and the integration of signals intelligence into military planning at every level. The bombs themselves vanish into history. Churchill orders all 211 British machines destroyed in 1945 to preserve secrecy. 2 machines survive, one preserved at GCHQ headquarters and one at Bletchley Park itself. Not until 2007 does a team of volunteers complete a working reconstruction of a Turing Welchman bomb, now displayed at the National Museum of Computing at Bletchley Park, where visitors can watch it operate and hear the distinctive clicking pattern that once meant lives saved and shipping preserved. The human cost of maintaining the secret proved significant. Alan Turing, arguably the greatest single contributor to breaking Enigma and a pioneer of theoretical computer science, faces prosecution in 1952 for homosexuality. Given a choice between imprisonment and chemical castration, he chooses the latter. On June 7, 1954, Alan Turing dies from cyanide poisoning, officially ruled suicide at age 41. He receives no public recognition for his war work during his lifetime. Not until 2009 does British Prime Minister Gordon Brown issue an official apology, and not until 2013 does Queen Elizabeth II grant Turing a posthumous royal pardon. In 2019, the Bank of England announces that Turing's portrait will appear on the £50 note, stating Alan Turing was an outstanding mathematician whose work has had enormous impact. The Polish cryptologists fare little better. Marian Rejewski, Jerzy Rakicki, and Henryk Zygalski escape Poland as Germany invades in 1939 and continue cryptanalysis work in France and later Britain, though the British never fully integrate them into Bletchley Park operations. After the war, Rejewski returns to Soviet-controlled Poland and works as an accountant, unable to speak publicly about his cryptographic achievements. He dies in 1980, recognized by cryptographic historians, but largely unknown to the public. Not until 2000 does Poland honor the 3 mathematicians with monuments and museums celebrating their crucial contribution. The breaking of Enigma represents more than a cryptographic achievement. It demonstrates the industrial application of mathematical genius, the power of international cooperation born from desperation, and the strategic value of information itself as a weapon of war. The mathematicians who solved Enigma's equations, the engineers who built the machines that accelerated their work, the operators who ran bombs through exhausting shifts, and the intelligence analysts who transformed decrypts into actionable intelligence together, created an advantage that shifted the course of history. The story reveals several profound lessons. First, no security system remains secure if implementation procedures contain weaknesses. The German practice of double encrypting message keys in the 1930s, the predictable phraseology in military communications, and the fundamental design flaw that prevented any letter from encrypting to itself. These operational and design weaknesses undermine mathematical complexity that should have made Enigma unbreakable. Security demands not just mathematical sophistication, but disciplined operational practice, which human beings cannot sustain perfectly across millions of messages. Second, the breaking of Enigma demonstrates that sufficiently important problems justify enormous resource commitments. The Allied powers devoted thousands of personnel, hundreds of tons of specialized machinery, and years of sustained intellectual effort to breaking a single encryption system because the strategic value justified the investment. Modern intelligence services and cybersecurity organizations continue this tradition, investing billions in capabilities to protect or penetrate encrypted communications. Third, the Enigma story highlights the essential role of international cooperation in confronting overwhelming challenges. Polish mathematicians provided the foundational methods. French intelligence supplied the critical documents. From Agent Ash, British scientists and engineers built the industrial-scale braking system. American manufacturing capacity produced the machines that finally conquered the four-rotor variant. No single nation possessed all the necessary components. Together, they changed history. If you found this story of mathematical warfare compelling, please like this video and share it with others interested in the hidden history of World War II. Leave a comment telling us where you're watching from. We love seeing how this history resonates across the globe. Subscribe to our channel for more deeply researched documentaries about the brilliant minds and critical moments that shaped the modern world. And consider supporting us on Patreon if you'd like to see more comprehensive historical content like this. These codebreakers polish mathematicians working in secret, British scientists building unprecedented machines, women operating equipment and analyzing patterns in cold huts, sailors dying to capture codebooks from sinking submarines deserve to be remembered. Their work saved millions of lives, shortened one of history's bloodiest wars, and laid foundations for the digital age we now inhabit. By watching and sharing their stories, you help ensure that their sacrifice and brilliance remain part of our collective memory. Thank you for keeping history alive.